Okay, let's do the same thing now with a breadth first search. So I've got another copy of the diagram. And I sort of find this a bit easier to do somehow with the breadth first search. We've done this before when we did the vertex colouring, the same idea. So we're now going to do a breadth first search, and my technique, there are lots of choices involved because you need to choose the order of vertices. And in the last example we had to choose which vertex we chose because there are often several adjacent vertices and you need to know which one you choose. And if they're labelled, you can choose it according to the value of the label. In this case, we have to put all adjacent vertices on the queue, but we're going to do it in ascending numerical order. So we're going to start at some vertex, or we're going to move to other vertices, but at each stage we add all adjacent, not just one, but all adjacent vertices, or any we can, to the queue. Let's say in increasing numerical order to be definite. E.g., I mean, you don't have to do this, but you need some convention in increasing numerical order. So if we start at 7, we add all the vertices this time that are adjacent to 7. So we add 3 and 12 in ascending numerical order. And then I have to record the fact that I've done 7. And it's probably a good idea to say we've scanned 3 and 12. And then we go to the next, it's a queue, you see, so we come off the queue this way. So 7 comes off the queue and other stuff goes on the queue. So strictly speaking, when I tick it, it means it's come off the queue. So tick means off the queue. So 7 is off the queue. That means the front of the queue, it's not like a stack. We always look at the left when we're doing the queue. The front of the queue is number 3. So 3 is adjacent to 2 and 9. And then we've done 3. 3 can come off the queue. And then we look at 12. Okay, because that's the next one. We're looking at 12 next. So 12 is adjacent to 8 and 11. And 12 is done. We go to 2. So we're sort of going zigzagging back and forward between the different parts of the graph. Then we're looking at 2. 2 is adjacent to 3, but 3's already been done. So we don't repeat things. Things don't enter the queue twice, things have come off and fallen down a pit or something. So 3 does not go on again. So 2 has been done. There are no, I should say all, if any. There may be none. In this case, there are none. So 2's been done. We go to 9. 9 is adjacent to 1 and 14. So this time we are seeing 14 from 9. So this edge is going to be included in our tree, I think. So 9 has been done. Then we go back to 8. 8, there's nothing more to do. Off the queue. 11 off the queue. Number 1 is adjacent to 4 and 6. 1 has been done. 14 is adjacent to 13 and 15. It's sort of more fun, this method, because you're sort of getting more into the graph somehow. It's broader, that's the idea, that's why it's called breadth first search. So 14 has been done. Should really strike these vertices off once they're in the queue, just so I don't make a mistake. 4, nothing to be done. 6, 10 is yet to be scanned, and 5. Sorry, I made a mistake. 5 should go first because it's lower than 10. That was 6 being done. 13, nothing more to be done because 14 is already there. I forgot to strike it off. 15 is adjacent to 16. And hopefully that's it. We don't need to go any more because we've got everything. 10 and 5 and 10 are there. So that is the queue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, with all 16 vertices. The stuff has come off the queue, but that's how the queue develops, so to speak. So if you want to see the sort of dynamical process of the queue, again, in the notes, you can see how this is done. You may prefer to do it with a table because you can easily make mistakes with my method. You forget that you've removed vertices, you get vertices twice, you mess it all up. So if you really want to avoid errors, you can use, or if you prefer to, you can use a table. So in this case, the table would look something like this. So again, you see we start with, you can't see that. You start with 7, then we add to 7 both of the adjacent vertices, both 3 and 12. And then 7 comes off the queue. So the actual queue is not the long great thing I had on the paper, but the queue never really gets particularly long. We didn't get this long stack like we had a long stack up to vertex 13. At most we've got 4 vertices in the queue at any time, because we keep removing vertices from the left. So the 3 came off, and we put the 2 and the 9, which are adjacent to 3. And then we got to 12 on the other bit of the graph, so that comes off the queue, and that's the vertex we use to look at its adjacent vertices, which were 8 and 11, and so on. So we just keep removing from the left. And if you look at the pattern of this table, you'll see that there are these diagonal lines. Unfortunately, the spacing messes it up on the left, but you see on the right-hand side, if you don't, you can easily check you haven't made a mistake, because all these vertices should sort of move, each one moves one to the left because it's moving up in the queue. It's like sprung up, like as there's a spring on the right-hand side. So you get these diagonals of numbers as the numbers move from right to left in the queue. So it's easy to check you haven't made a mistake. Okay, so what we need to do is we need to construct the tree that corresponds to this search. And as I indicated, it's going to be slightly different, because this time we did use this edge here. Not sure what edge we didn't use, but we'll see in a moment. Well, I might need my table to actually check that. Let me see if I can fit the tree on here. So it's going to be broader, so there's some hope I might be able to do this. So we start with 7. And then 7, of course, was adjacent to 3 and 12. And then 3 was adjacent to 2 and 9. Let's put the 2 there and the 9 there. And the 12 was adjacent to the 8 and 11. And then the 2 was adjacent to nothing. The 9 was adjacent to 1 and 6. No, that's rubbish. The 9 was adjacent to 1 only. And then the 1 was adjacent, then where have I got to? The 8, nothing. 11, nothing. The 1 was adjacent to 4 and 6. You still see that? And then 14, we actually got to 14, but I've left, why did I leave that out? Because 9 was adjacent to 1 and 14. It's 14, I should have put that. And then the 14 is adjacent to 13 and 15. So I've come up to there now. And then the 4 was adjacent to nothing. The 6 came after 4, was adjacent to 5 and 10. And the 15, 13 adjacent to nothing, 15 was adjacent to 16. So I think that's the tree there. So what edge is missing? How many edges? This is, have we got all the vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So again we have 16 vertices because it's a spanning tree. Therefore you must have 15 edges. I won't have to count them up. It's a tree, obviously. There are no cycles. What edge is missing? I've just spotted it's not so easy. What edge? It has to be one of the edges of the cycle, right? Because the cycle has to be broken. Before we broke it by removing the edge from 9 to 14. Which cycle has been broken to get this tree? Which edge has been broken to get this tree?
10 to 15?
Yeah, 10 to 15. So this is the broken edge. So the edge 10 to 15 is missing in the tree. We know that we can't have a cycle, so one of those edges has to be missing. And you see that tree is shallower in the sense that if you want to go from top to bottom, you've got 3 leaves all at the same level, and that's level 1, 2, 3, 4, 5. Okay, so we've only needed to go down 5 levels. Okay, so the height of this tree, the number of levels, if you like, that means I'm sort of selecting that as the starting point. It's height 5. To get from 7 to any other vertex requires no more than 5 edges. And that's because it's broadened out. We've got sort of more edges. We've got, in fact, 3 edges, whereas before I think there was only 1 at distance 8 from the start. This time there are 3 edges, 3 vertices at distance 5 from the start. Maybe I should just say that the tree, to sort of remind you this, the tree, whether it be the depth first search or breadth first search, the tree includes, if you like, includes the edges, only those edges. So if the graph is very complicated, very connected, you'll lose a lot of edges. In this example we only lost 1. The tree includes only those edges representing adjacent vertices used in the search. That's how you form the tree.